Welcome back, listeners, to another exciting episode of Operating Systems Crashcast. I'm Victor, and today we're diving into a crucial aspect of process management, Interprocess Communication, or IPC for short. Joining me as always is the brilliant Sheila. How are you doing today, Sheila?
I'm doing great, Victor. I'm really excited to talk about IPC today. It's such a fundamental concept in operating systems and multi-process environments. Shall we jump right in?
Absolutely. Let's start with the basics. Sheila, could you give our listeners a quick overview of what interprocess communication is all about?
Of course, Victor. Interprocess communication, or IPC, refers to the mechanisms an operating system provides to allow processes to communicate with each other and synchronize their actions. It's like how co-workers in an office need to share information and coordinate their efforts to complete a project.
That's a great analogy, Sheila. And just like in an office, there are different ways for processes to communicate. The two main models of IPC are shared memory and message passing. Can you elaborate on these?
Certainly. In the shared memory model, a common section of memory is established that processes can read and write to. It's like having a shared whiteboard in the office where anyone can write or read information. On the other hand, message passing involves processes exchanging messages with each other, similar to sending emails or instant messages to colleagues.
Excellent explanation. Now let's dive a bit deeper into these models. What are some key differences between shared memory and message passing?
The main difference lies in how data is transferred. Shared memory is generally faster because once the memory is set up, processes can access it directly without involving the kernel. However, it requires careful synchronization to prevent conflicts. Message passing, while potentially slower due to kernel involvement, is often easier to implement and can work across distributed systems.
That's a crucial point about synchronization, Sheila. It reminds me of the classic producer-consumer problem. Could you explain this problem and how it relates to IPC?
Absolutely, Victor. The producer-consumer problem is a classic example of IPC challenges. Imagine a scenario where one process, the producer, is generating data, and another process, the consumer, is using that data. They share a fixed-size buffer. The producer can't add data if the buffer is full, and the consumer can't remove data if the buffer is empty. This scenario highlights the need for synchronization in IPC to prevent issues like race conditions or deadlocks.
That's a great explanation, Sheila. It really illustrates the complexities involved in IPC. Speaking of complexities, what are some of the main challenges developers face when implementing IPC in real-world systems?
One of the biggest challenges is ensuring proper synchronization, as we discussed with the producer-consumer problem. Developers need to carefully manage access to shared resources to prevent race conditions, where the outcome depends on the timing of events. Another challenge is dealing with potential deadlocks, where processes are waiting for each other indefinitely. Balancing performance with the overhead of synchronization mechanisms is also a constant consideration.
Those are indeed significant challenges. Despite these, IPC remains crucial in modern computing. Can you give our listeners some examples of where IPC is commonly used in today's systems?
Certainly. IPC is everywhere in modern computing. It's used in multi-threaded applications where different threads need to communicate, in client-server architectures for communication between the client and server processes, and in microservices architectures where different services need to interact. Even in your smartphone, various apps and system processes are constantly using IPC to coordinate their actions.
That really puts into perspective how important IPC is. As we wrap up, Sheila, what would you say are the key takeaways for our listeners about interprocess communication?
Great question, Victor. I'd say the key points to remember are: first, IPC is essential for coordination between processes in an operating system. Second, the two main models are shared memory and message passing, each with their own strengths and challenges. Third, proper synchronization is crucial to prevent issues like race conditions and deadlocks. And finally, IPC is ubiquitous in modern computing, from multi-threaded applications to distributed systems.
Excellent summary, Sheila. And for our listeners preparing for interviews, Remember that understanding IPC is crucial. Be prepared to discuss the differences between shared memory and message passing, explain synchronization issues, and provide real-world examples of IPC in action. Thank you all for tuning in to Operating Systems Crashcast. Until next time, keep those processes communicating.